Okay, so now we're done with the pre-processing. We're ready to import layers and models from Keras and build our model. So here there's no real surprise. I've mentioned this into the preparatory video, and we build the model, and all these numbers should look familiar. Yeah, we're gonna have 4 Covnet layers. The filter size is going to be 3 by 3, and we will do 2 by 2 max pooling. And we've seen that the number of channels goes from 32 to 64, and then 2 times to 128. The activation we will use is ReLU, so no surprise here. And here you see the input shape, which is a color image. That's why we have this tree. And the pixels is 150 by 150. At the end, we flatten our last image, and then we added here a dropout layer. It's something that I did not mention yet, but we're gonna add a dropout layer. And then we've seen that our dense layer is 512 units. Activation is still ReLU. And at the end, you have a sigmoid activation, and that will ultimately decide or predict if the picture is a cat or a dog. So let's run this. Okay, so now let's import Keras optimizers and compile our model. So this is the block of code. No surprise, it's binary cross entropy because it's a binary classifier. And in terms of optimizer, we're gonna use RMS prop with a learning rate of 10 to the power of -4. And we will use accuracy as a metric. Accuracy is an okay metric here because our data set is balanced. It's completely balanced. So let us run this block of code. Here we go. All right, so let's now introduce a new concept called a generator. A generator in Python actually works like an iterator. Yeah, the only difference is that it will loop indefinitely. So you will need to tell the system when to stop. So let me paste the block of code. And remember here, this we do. Basically, this takes care of the conversion of the JPEG files into tensors. Remember, we said this would be taken care of by the image data generator. And the image data generator also rescales the pixel intensities. So all pixel intensities in the tensor will be between 0 and 1 because we divide by 255. Yeah. Now, why are generators used? Well, it's a memory issue. If you have big data, it might not be possible to load a large amount of data at the same time to the computer. Yeah, a generator actually allows you to train your machine in pieces and feeds these pieces to potentially multi-cores you have on your machine. The only drawback here is that generators, they will loop indefinitely. So you will need to tell the machine at some point when to stop. All right, so here we created 2 generators, a train generator and a val generator. And remember, when using the flow from directory method, we actually go to a directory that has 2 subdirectories. Yeah, and the subdirectories represent the different classes. In our case, the classes are cats and dogs. And in our directory training 2000, we have 1,000 training samples of cats and 1,000 training samples of dogs. So this is target size. This is 150 by 150, correct? And we will take a batch size of 20. So in this case, we will use mini batch stochastic gradient descent with a batch size of 20. All right, so let's run this code. And here we are. So this is correct. The train generator, there's 2,000 images and they belong to two classes. That's correct, cats and dogs. And the same for validation, two classes, cats and dogs. But here we only have 2 times 500 images. So that's 1,000. That's also correct. Okay, so now let's compile our model with this line of code. So here we do a model fit generator. Yeah. And basically this is the train generator here, and step per epoch is 20. Basically we have 2,000 training samples, and if we feed batches of 20, we finish an epoch after 100 steps. Yeah, because remember, a generator doesn't know when to stop. So if you tell it to take 100 steps of 20 batches, this will mark the end of the epoch. We're gonna use 30 epochs, so we're gonna loop through all the training data 30 times. And then for validation, we use the val generator. And of course, if we only feed the system with batches of 20, you will have, of course, 20 validation steps in that batch. All right, so let's run this code. And here we start with epoch number 1 out of 30. And you can see here the processing of this training data. So as you can see, this will take a while. All right, so we're done now, 30 epochs. And first thing we're gonna do is save our model. And we know that the fit method, the model fit, doesn't matter if it's a fit or fit generator, will return a history object that contains all the information about the epochs, right? So this is information we're going to be able to use to plot our valuation accuracy with respect to the training accuracy. So this block of code we've already used when we discussed the dense neural network. So basically we can just copy this. All right, so I define my epoch range, and now what we will do is plot. Yeah, we will plot the training accuracy and validation accuracy with respect to the number of epochs, and we will do the same with training loss and validation loss. This code is exactly the same as we used when we discussed dense neural networks, so you can just copy and paste, and let's run it. Should give us 2 beautiful graphs, and here are the graphs. We can see that the validation accuracy, and we're mainly interested in the validation accuracy, is actually reaching a maximum here. And when we go through the table, we should be able to find that maximum. So I see here 75.5 is the highest. Here I see 77, the highest. But here I find 78.25. Yeah, it will never go above that. All right, so that's clearly a sign of overfitting. And if we look at the loss, the validation loss reaches its minimum roughly around 14 epochs, but it's already very close to that as well after about 11. Yeah. So yeah, and you see the loss is going up again. Yeah, so this is clearly a case of overfitting. That should not surprise us because in the end we only used a training set of about 2,000 pictures, and we also used one dropout layer. But you see, we could not prevent the overfitting. And actually what we're gonna do now is we're gonna learn another mechanism to fight overfitting. and that is called data augmentation. Data augmentation is interesting in the case when we have only small data sets.